So what we're now going to do is we're going to use this for Gaussian processes. So the idea is that it's not just height and weight, but we can just use this to model arbitrary correlations between observations. So what we see here is, well, here's some kernel, and it's actually called a factor analysis kernel. And this is now a sample from that corresponding object. So a Gaussian process is just like a normal distribution with mean and covariance, except that it's now defined on a possibly infinitely large domain, where for any finite set of locations where you're going to measure things, you will get your corresponding normal distribution with mean and covariance. And that covariance matrix is going to be given by a covariance kernel, which just so happens to be the same kernel that we used in kernel methods for the past few weeks. So, in other words, instead of this fixed set of variables, we now have some larger domain, like pictures of images, and then we define a stochastic process on pictures of images, or I don't know, different types of blood samples or whatever, and we want to predict something using them, and so we can use some mean function and a covariance function, and that's it. So in pictures, what we might do is we might have a couple of locations where we go and measure things, and we assume that the values at those measurement locations are drawn from, are jointly normal. So think of a stochastic process like a function, except that each time you invoke the function, it gives you a different random number back. Right? So, think of it like, your C++ function. Each time you invoke it, it gives you another random number back. And if you can invoke it with an arbitrary number of arbitrary set of arguments. Each time it'll give you a random number back. If you want to ask, what's the correlation between those outputs that you're getting, well, that's given by the corresponding covariance function and the corresponding mean. So this is an important distinction. We are not estimating functions here. We are actually just looking at correlations between evaluations at locations. So here's why you have to go through this technical distinction, and this is something that mostly mathematicians care about and not so much anybody else. Basically, if you have a Gaussian, you need to normalize it. And if you have an infinite dimensional Gaussian, you can't normalize it, right? So that's why you always have to make this very careful dance about finite dimensional objects. And that's why we have to introduce what's called a Gaussian process rather than just talk about the normal distribution on all function values. That's the one and only reason why you have to do this. But everything else goes through just like we had a Gaussian before. In some very, very simple cases where this function space is very low dimensional, for instance, it's explicitly parameterized in a linear form, like what we did actually in one of the assignments, then again you can go and actually explicitly get this, but that's very rare. Okay. So here's a couple more samples from such a Gaussian process, and if you look at it, it just looks like a distribution. But it's not really, it looks like these look like functions, but they're not really functions. They are just, samples from the Gaussian process, and they're just, evaluated at each of those points. So, subtle difference, but if you look at it from far away, you won't see it.
Why is it continuous?
Why is it continuous? Good question. They don't actually have to be continuous. You can design Gaussian processes that are not continuous, but I just made my life easy and picked a particularly nice kernel for which it looks continuous. But you might know another one that is not is not smooth. So for instance, a random walk or a Brownian bridge. So a random walk kernel, a Brownian bridge kernel, will actually not be differentiable. But of course, any particular realization of this random walk, well, you just take a step each way. Well, it's going to, have bounded changes within a given range. But yeah, so they don't have to be. Very good question. And so what we do is we just say again, well, look, let's pick a mean and a covariance function. And so quite often you set the mean to be 0 if you don't know any better. Don't do that in a real engineering problem. Pick the mean to be what you would expect it to be. Right? So you can use some previous engineering for that. And then the covariance function k is just given by your kernel. And that's it. Okay. And so this is exactly what we had with kernels. So we basically, have a function of 2 arguments. We get the matrix with non-negative eigenvalues because these are covariance functions. And describes the correlations between pairs of points. And yes, guess what? It actually happens to be exactly the kernels that we've been working with for quite a while. And that's really all you need to know to make this operational. So what you'll now get is one of the best regression estimators that you can design, and it's very easy to implement. Okay. So remember, for inference, what we did is we looked at, p of weight given height, stuff like this, and we needed to look at the covariance functions and the means. So this is exactly what we had before when I talked about the Schur complement. This is basically, the covariance, conditional covariance. This is the conditional mean. It's conditioned on, well, the deviation between observations and that really mean. Okay. And if you set the means to be 0, then, of course, what happens is this goes away, and this goes away, and you just have ktt prime, ktt inverse times t. And what you usually do is you pre-compute that yellow block in one go, and now it's just matrix times vector to predict. Okay. The good thing is the predictive uncertainty is really independent of t. Well, this is really nice for experimental design because what you can now do is you can place your measurements in such a way that the aggregate predictive uncertainty is fairly small for a lot of locations. The bad thing is the predictive uncertainty is data independent. In other words, the model doesn't care how well it actually fits to the data in coming up with an estimate of how well it'll fit future data. And that's horrible, right? So imagine, for instance, you take exams and you always think you're really, really horrible at the exams, but then it actually always turns out you aced them. Then any reasonable human would say, well, look, you really shouldn't panic that much about the exams because you're going to be fine anyway. But if you're a Gaussian process, you will still be panicky and paranoid and worry about doing poorly in the future exams. Right? So predictive uncertainty does not adapt to the data. That's the key weakness. One way of fixing this is then by actually also inferring the covariance function itself. We may not actually get to a lot of that. You've done a bit of that in the context of model selection, of tuning the kernel parameters. That's basically what you're doing. Okay, so here's Gaussian process regression in the linear case in one slide, because here the covariance matrix is just X transpose X. And we all saw that already before. Right? And you can actually see that there's something very seriously wrong with that expression. Right? So if you look at it closely, so this is our covariance function. It's just X prime transpose X prime minus X prime times X transpose X, so basically minus this block here. And that is nothing else than a projector onto the space spanned by X. So the bad thing is that, well, once I have enough X's such that they span the entire space, then this thing here can become 0. In other words, I then proclaim that I will know with certainty what my next observations are going to be. That is stupid, right? Because this is just supreme overconfidence. So how do we fix it? Well, the way to fix it is to assume that, well, I didn't really observe maybe the variable that came from a Gaussian process, but it was perturbed by some additive noise. So what I do is I take the degenerate covariance, and then I say, well, actually, rather than observing this, I observe some y's. So t is drawn from a GP, but y isn't. Well, actually, y, we'll see, will also be drawn from a GP, but basically, you just plot that covariance matrix. And yep. I'm doing this in a very simple way. I'm just using additive noise. So now what happens if I add two Gaussians? Well, if I add two Gaussians, I get another Gaussian, right? The same thing happens here. If I have the t's drawn from a Gaussian process, and then I have the y's drawn from the t's by adding, additive noise, I get another Gaussian process. And the key thing is that here, simply rather than having just, covariance k, I get covariance k plus sigma squared identity. Right? So, in other words, the means add up, and since I add 0 mean, nothing happens. But then the variances also add up, and so I get the covariance matrix plus sigma squared times the identity, because I'm adding independent Gaussian noise. Okay. So this was an important trick that we used, and people have used this trick a lot. So when you have a real set of observations that don't quite fit your model, so you have this beautiful model, like, everything is Gaussian, and you have reality, and unfortunately, reality and the model don't quite fit, then you say, well, let's assume that there's something else in addition to my model going on, and I'll just, assume some form of a link between reality and the model. The simplest form of a link is to say, well, we just added some Gaussian noise. Slightly fancier ways that you could use is, for instance, if you have, binary observations, and I want to match this into a Gaussian, I could have like a logistic transfer function. So there are lots of ways how you can turn something very nice and tractable into something that may not have a terribly good mathematical representation at all. And in decomposing these problems, we've just seen the first example of that, I can actually model very complex phenomena. So for instance, there's absolutely no reason why, for instance, natural language should be Gaussian, right? Because, it's just, I either utter a word or I don't. So there's nothing, I utter 0.05 of a word. Well, that doesn't happen. Then I'm slurring and I'm drunk. So therefore, having this link between real observations and my model is what will let me apply my statistical estimators to a much larger set of problems than what you would get otherwise just from these very restrictive assumptions. The key point, though, is it's just a model, so don't always believe that your model is the truth. Okay. So this is quite dangerous. Sometimes people get too enamored by the math and then they actually believe it. Yeah, I've seen that a lot. So in any case, this is our covariance matrix. And now what we do is we just plug this in exactly the same way as before. The equations are identical. Just wherever we had k, we now have k plus something on the main diagonal. Here's some data. Here's the predictive mean. And, well, Here's the variance. And if you squint really, really hard, so this is just a predictive, I've just plotted the mean plus or minus the variance, right? It's here. And what you can see is that the predictive variance is larger out here. And it's also large here. Why do you think that happens? Yes? Exactly, because I have no data. So therefore, there's nothing to reduce my variance. That's exactly what happens. So this allows you to get, more confidence where you actually observe a lot. And the blue line is what actually the underlying function was. This was basically just a sine function. And yeah. Here are the details. This is basically just as I mentioned before. Wherever we had, predictive noise, we now have, predictive covariance, we now add this thing on the diagonal. And you can see two things happening from this. First of all, this prevents your variance ever from going to 0. And this basically also tempers the Schur complement by adding something in the matrix inverse. That also means that now the conditioning of your matrix is a lot better, because you just bumped up the smallest eigenvalue. Okay. And here's the entire pseudocode. So if you ever need to implement this, okay, so all you need is access to something that computes a kernel function. You just throw that in, and yeah, basically it's 7 lines of MATLAB or Python code, and you're done. Yes?
I think MATLAB actually does use Cholesky to solve that because of positive definite.
Often it does. Whenever MATLAB is smart enough to realize that you're dealing with a positive definite matrix, it will do that. The problem is that MATLAB isn't always very smart for 2 reasons. First of all, because it's not very smart. Secondly, because it often cannot be very smart. Because if you give it an arbitrary matrix, poor MATLAB has no chance of knowing that it's a PSD matrix. So this is why you quite often actually want to implement such things on your own, or at least use a dedicated implementation where that code then knows that it's PSD. And then the unfortunate thing is MATLAB, at least until recently, I don't know whether it's changed and become less horrible, was not able to deal terribly well with first taking a matrix, factorizing it, and then performing a Cholesky solver. Quick question, does anybody know what the complexity is for computing a Cholesky factorization? Is it linear, quadratic, cubic, quartic, quintic? Who opts for linear? Who opts for quadratic? Okay. Who opts for cubic? Who opts for quartic? Basically 4th order. Okay. The cubic guys have it, so it's cubic. Yay. Now, once you factorized it, how expensive is it to solve a linear system? So if I basically triangular matrix times vector equals something else. Is that linear? Is it quadratic? Is it cubic? Is it quartic? Well, yeah, okay, and a lot of you aren't quite sure. That is quadratic then. Yep. So basically, that's, it ought to be cheaper than the original problem, because otherwise why would you do the intermediate step of Cholesky factorization? But basically this means if you want to solve a linear system with a positive semi-definite matrix, never, ever compute its inverse, always only compute its factors, and solve the linear system on demand. The other thing that you can do is then, if that linear system has very bad condition number, you basically solve it forward, you look at the backwards residual, and you iterate. And the good thing is that good linear algebra packages will do that for you. You don't have to worry about this. So basically, never, ever do inf of m times x. Never, ever do this. This gives you horrible results. Because then poor MATLAB doesn't know what you're doing. It'll actually, compute the inverse as it's been ordered to, or to octave for that matter, and then multiply it. And this gives horrible results. Okay. Now, last, just connecting this into between support vector machines and Gaussian processes, basically, we just had a linear model in feature space in an SVM and a GP. We just looked at covariance functions. That actually works out to be the same thing, because if you look at the covariance when you have a normal distribution over all your parameters, you get exactly the kernel out of it. And I'm almost getting kicked out of this room, so we will do Gaussian processes next Monday, just very briefly, before we'll go to graphical models. So the operational summary is you take your covariance matrix, you improve its conditioning number by adding something to the main diagonal, and then it's a simple matrix inversion to solve this. And this is great up to what size? Okay. What size do you think your computer can easily handle if you do it in the form that I described right now? Okay. Any guesses? Your laptop. So let's say you have a laptop with 4 gigabytes of memory. What problem size do you think you can handle?
About 10,000?
10,000 is pretty right, yes. So if you're really good, maybe you can do 20,000, and you have to work quite hard already for that, but 10,000 you can do comfortably. 10,000 for the simple reason that this is basically then 10 to the 8 entries for the matrix, right? And 10 to the 8 entries for the matrix, if you use double, requires 800 megabytes. Then, if you store your Koleski matrix and all of those terms, it costs a little bit of extra as well. So 10,000 is comfortable. I mean, your computer will take a long time to do it because runtime is super linear in the size, but you can do it. Once you go to much higher dimensions, you need a lot of approximate function spaces. People have done a lot of work on that. If you're interested in how to do this, you can go to Archive and search for something called fast food. This is, I think, right now the fastest solver that you can use for that. So we did this at Google, and it was, quite fun. Okay, so this is all I have time to talk about today. On Monday, we'll do the GP classification. Come to the recitation if you want to see how the exam should have been solved. And the homeworks are out. At least homework 7 is out. Homework 8 will be out very shortly.
Good idea of when the finals will be.
The final is already announced on the website.
Is it? It
Yeah.
just says TBA.
Yeah. Okay, I'll need to